program. So this talk will be concerned with out-of-equilibrium dynamics and a unifying view on many-body localization. A more poetic title of this would say be 10 people in the room, 10 opinions on many-body localization. But, well, I should have known better. Last year I gave a talk with precisely that title, realizing and appreciating only in retrospect that with 10 people in the room it's utterly unrealistic to have 10 opinions on the subject matter, which is why I had to change the title again anyway. So this is the last talk of this beautiful program, and it goes without saying that this comes along with good news and bad news. The good news is that we've seen excellent introductions to the field, so I can be short on the introductory side. The equally obvious downside is that many of the topics that I will talk about in this talk will have already been touched upon in one way or the other during this week. We've seen the beautiful talks on many-body localization by Romain and Uli, like early this week. We will have a look at non-interacting fermions, at least a bit touching upon the theme of Maurizio and his tuplets beauty. There will be ideas of integrability touched upon a la JS or Pasquale. Matrix product states, matrix product operators will feature. So tensor networks ideas as Ignacio has explained them. Notions of thermalization will be touched upon a la Benjamin in his nice talk. Then of course I have to steal the copyrighted picture of John that he complained about, rightfully so. And we will also at least touch upon ideas of Gaussification as Jörg has beautifully explained them, I think yesterday morning. So here we are in this talk. So, but it's the hope that nevertheless we will have a kind of a new twist and mindset to the story when we meander through the theme, but let's see how it goes. So the starting point question of all this is a very familiar one, surely within this workshop, which is how quantum many-body systems eventually come to equilibrium. So how do they come to rest once pushed out of equilibrium, and how do properties like temperature in one way or the other dynamically emerge? Specifically, if one thinks of like a quantum quench, how many Google hits is that again? Like several hundreds, right? Somebody counted that. So if we quench a many-body system out of equilibrium, then one can ask what happens if you look at the non-equilibrium time evolution forever and ever for longer and longer times. And we can ask, does it equilibrate after all? I mean, how can it? It's a closed system after all. But, well, in the meantime, we nicely and well understand that, yes, such systems nicely and smoothly do relax. Of course, not the entire system can relax. It's a closed system after all. But what can happen, and this is what generically happens, is that local expectation value appear relaxed. So if you look at a local expectation value, it will initially wobble, and will soon become stationary and will take the value of the infinite time average. It's kind of self-averaging, and systems would nicely and locally nicely and smoothly relax to a apparent equilibrium state, which in turn is the maximum entropy state given all exponentially many constants of motion. So this is, I mean, the surprise value is very little. This is very well understood, and this is also provably true in a number of senses and fine prints. Specifically, it's true in expectation in time if the degeneracies of the eigen values of the many-body Hamiltonian are not too wild. But there's also a number of other senses in which this is true. Now, if one quenches to an integrable model, linking again to a theme that has popped up several infinitely many times over the week, then one would expect not only an equilibration but a convergence to an apparent stationary state, which is the so-called generalized Gibbs ensemble, so a maximum entropy state given only a few kind of well-chosen integrals of motion. And there's rather little to add on this from my side today, except I would like to highlight a kind of cute addition to the theme that we just put out like last week on the preprint server, that's kind of new and fresh, and at the same time builds upon our earliest contribution to that question from 2008, which is like a convergence to a generalized Gibbs ensemble for non-interacting theories, which is kind of, I quite like it because it's a new proof, and it's a kind of cute way or a clean way of stating the assumptions that go in. I hope this is fair to say. So the point is, the only thing you need is you have some initial state. That could be a high temperature state, it could be a ground state of a strongly correlated model, and actually on any lattice, any graph, some state whatsoever, except what you want is short-range correlations. So say clustering correlations that Benjamin has explained nicely in his talk, well, say ground state of a gap model or something like that. And then you look at the evolution under some non-interacting Hamiltonian that has transport, meaning you put particles here, and at some point later there will be wherever in the lattice. So that's it, short-range correlations and transport. And with these assumptions alone, and not more, one can show not only convergence to a generalized Gibbs ensemble, but in fact with all glory and beauty and bounds and time scales. So one could say things like, for an arbitrarily small error epsilon, one would really learn the time interval from the relaxation time on until the recurrence time, for which you know that the local expectation values take precisely up to that error the value of the generalized Gibbs ensemble state. So this is like with error bars and timescale information, one would exactly get this convergence to a generalized Gibbs ensemble. And this happens again to be a Gaussian state given the second moments. So not only does it equilibrate in time, but it kind of Gaussifies through incommensurate mixing, the higher cumulants go away and the state becomes presumably like a Gaussian state given the second moment. It's like the argument is like long and winding and involved. At the heart of it is the kind of a logic of a Lindeberg central limit theorem that's like formulated for fermions, but the same logic also applies to boson. It is kind of nice that it's a very kind of general principle that through incommensurate mixing you would get this Gaussianity coming about and the higher cumulates going away in time, quite in the same way as Jörg has beautifully explained yesterday in his talk when he looked at this quenched field dynamics, where the non-Vicky, can you say that? The non-Vix theorems correlation functions become like in the Vix theorem if you go over time close to the non-integrable setting.
Gaussianification just because you're finite Hamiltonian quadratic.
Yeah, exactly. So the Hamiltonian is very special. It's quadratic, boring, non-interacting, but the states are very general, so to say. They can be grounds for interacting models, like funny states. So that's the logic, indeed. So it would be trivial if the states would be Gaussian as well, but it's like a large class of states, but a very special class of Hamiltonians. You're absolutely right.
But not all states Gaussian.
Well, I mean, here it's formulated as a kind of this cluster of correlation states, but you can relax that condition also a bit.
So what does it mean as clustering correlation?
Well, short-range correlations. Yeah, like, I mean, a ground state of a gap model would have that. Or high temperature states, as Benjamin also touched upon, these type of states. Yeah, so that's the...
Now, is that the following thing a counterexample? I create a 4-photon entangled state, and that propagates, and this propagation is a function. But it always, I can always reconstruct that.
Sure, it's not, they would not be short range initially, that's the thing. I mean, you think of a down, we discussed it. Yeah, but it's not geometrically local. It's like this kind of down conversion type experiment that you mentioned in Vienna, right? No, but that would mean, you think of a lattice model like geometrically local condensed matter type short range correlations. That's what I mean.
Is Hamiltonian allowed to have long range interactions?
No, it's it can have long range, indeed. You're absolutely right. It's free. I mean, it's just that. There's nothing swept on the carpet. It's free. It's quadratic, but it's not hopping. It can be like a 7-ranged Hamiltonian or even long range, as long as it has transport and is quadratic. Yeah. So it is what it is. I mean, Actually, that was just a teaser. That's not the topic of my talk. So if I...
No, but it basically means it depends on which correlations you have in the beginning.
Yeah.
For example, the ones that have a, if you measure non-factorizing correlation functions, it doesn't have to be.
Yeah. I mean, of course, if there's some hidden long-range structure initially there, then that might remain.
It will stay, right?
Yeah, I mean, well, yes and no. I mean, asymptotically.
He doesn't want to commit on this table.
No, that's what it is.
Experiment, you know.
I totally commit. Like, okay, for arbitrary ranges of correlations, it will still be asymptotically true, but of course it will happen later. If you have like 10 kilometers of correlations initially, then you have to look for a longer system, larger system to eventually Gaussify, but then it will also do, because that's the assumption.
If the light cone basically would cover all the range of the initial correlations, then it Gaussifies.
Exactly, that's what I mean. Yeah, indeed. And even your example does. So, perfectly right. That's what it is. Oh, great. I mean, it's great to have so many questions, but
Just I have two comments. First of all, that I think on basis of exact calculation that your clustering with exponential is far too strong.
No, I agree, but I put this for pedagogical reasons, because you can replace it by suitable power laws. In fact, I even know the powers. Like in 1D would be 1 over squared, and generally like 1 over graph theoretic dimension to the power of graph theoretic dimension plus 1, which is enough. You're absolutely right. So this is like a clean way of putting it for pedagogical reasons. I agree.
That for boson we have done some work exactly on the same lines.
Yeah, I know. I mean, you have been cited on the previous line. Yeah. I mean, also our work is from 2008 for bosons. I mean, sure, that's almost long time ago. Yeah. But here, what is a new proof technique is kind of a clean way of saying it with very stringent assumptions. So that's what I like about it. But I mean, it stands on a large body of literature by me for that matter. I mean, there's a lot of stuff on the thing. Good. So do systems also thermalize? So on top of equilibrated, becoming stationary in time, does it become thermal through its own dynamics? There's no bath. Does it kind of thermalize, or again, more precisely, look locally as if the entire system had thermalized? Yeah. And there's a lot to say about this, but I will cut my tongue today.
I think you cannot say that if you only look locally that the entire system is thermalized. You can only say something about the local sizes you get.
Yeah, that's what I said. That's what I said. When I say O is locally compatible as if the entire system had thermalized, when I say this, I mean, of course, not the entire system can thermalize, there's no bath, but it can look for the overwhelming majority of times as if the entire system was in a Gibbs state, reduced to your state where you look at. That's precisely what I mean. Yeah? And there's a lot to say about this, I think, but I will cut my tongue. I will not do it today, otherwise we will get nowhere. I think this question is not fully settled, at least not on the level of the rigor of mathematical physics. I think Benjamin nods his head. At the same time, it's true that most people will probably agree that if you have a non-integrable model, then the general physics expectation is that if you quantum anybody's system out of equilibrium, that eventually will just form its own heat bath, as people say, and will eventually thermalize. So it's a bit of a matter of like precisely understanding with the pedantic head what's happening on the physicsy side. This is what people usually take for granted. Non-integrable model would thermalize in time. In particular, thermalization follows from the so-called eigenstate thermalization hypothesis that has been mentioned already a couple of times over the week, which argues that thermalization can already be discussed and argued about on the level of individual eigenstates of the many-body Hamiltonian. And indeed, if this is the case, if already individual eigenstates locally look thermal in the sense as Jörg has just rightfully pointed out, then it's indeed possible to show that you have thermalization. Except that, again, I mean, it's a bit of a, don't get me going, it's a bit of a curious type of hypothesis. It's very hard to check, even numerically, with exact diagonalization. It's also a bit too strong to prove thermalization, also a bit too weak at the same time. It's not expected to be true at the bounds of the spectrum. Benjamin has nicely explained this in his talk. Having said that, swiping that under the carpet for now, I think most people, like on a physicsy intuition, would say that it's reasonable to assume that the eigenstate thermalization hypothesis is valid to a good approximation for our non-integrable models. I would think this is the common physicsy intuition that the eigenstate thermalization hypothesis would be true largely for non-integrable models. There's progress on this question, but I will swipe it under the carpet. I will make use of a shameless advertisement, say, of 2 reviews that we recently wrote on the subject. One is more physicsy on quantum many-body systems out of equilibrium, more focusing on like cold atoms and optical lattices, and on top of atom chips on this more physicsy side. And then there's this monster of equilibration, thermalization, and the emergence of statistical mechanics in closed quantum systems, which is a long, more mathematical physicsy article that covers most things that are known on these questions to date. I send out the proofs today. If you have like complaints of some sort or a citation wishes, do so, but please do so today. So this will really be settled now. So this is, I relate these questions today. So I think the point I'm going to make here is that if you quench a many-body system out of equilibrium, many people would argue that it's a reasonable expectation to think that a system would, in the long run, form its own heat bath, would thermalize, would come to rest, and would locally appear as if the whole thing had thermalized to a Gibbs state. This is kind of how temperature emerges in nature after all. Although Jörg is of course right, it doesn't really thermalize, but it looks as if it had thermalized. Now, there are systems that, much to the puzzlement of statistical mechanics people, condensed matter people, and others, that stubbornly do not thermalize. That just don't do it. You can quench, they will eventually equilibrate, so look like the infinite time average, but they will not do so to the Gibbs state given the energy expectation, but they will kind of get stuck along the way. They are not going to the right thing. So they will not serve as their own heat bath in the way, and the candidates of these types of systems that remain too much memory of the initial condition, and not for long times, but in fact for infinite times that will have an infinite time memory of where they came from, are so-called many-body localized models where interactions on the one hand and disorder on the other hand in an intricate way come together and come into play. And this is where the rest of the talk will be staged. We look at many-body localization from different angles and view where disorder and interaction come together. So how about disordered models after all? This is not my kitchen. Don't worry too much. Okay, so the mother of all disordered models is this one, the Anderson model, going back to seminal work of the 50s by Anderson, that describes the hopping of a single particle on a line subject to an IID random potential with respect to a meaningful probability distribution. This model is overwhelmingly understood on the level of physical understanding and intuition. It's very reasonably well understood on the level of mathematical rigor in the study of random Schrödinger operators, and it's very clear and known that such systems localize. This is true in several senses of the term. In particular, it's true in the sense as one can call like static reading of localization, which means that not only the ground state, that would be true for any gap model, but in fact all the way up the eigenstates of the many-body Hamiltonian, or in this case single-body Hamiltonian or equivalently non-interacting fermionic particles, all the energy eigenvectors will be exponentially clustering away from the main diagonal, or at least have that property with very high probability that increases with the system size. So eigenvectors, not the ground state, but all the way up, will have short-range correlations precisely in the way, this kind of cluster of correlations way that I have mentioned earlier at the beginning of this talk. That's kind of the static reading of localization. Then there's the more operational, dynamic reading of localization, where you say, okay, you put a particle somewhere, where does it go? What happens? And it can hop a little bit, left, right, it will hop here and there, but it will eventually get stuck in the sense that it will hop a couple of sites away, but there will be a bound that is uniform in time and exponentially suppressed in space, meaning uniformly in time it might go a couple of sites, but then will get stuck and will kind of dynamically localize in the lattice. So there is no particle transport, things get stuck, particles will not get through, even energetically they in principle could, but that's the point of Anderson localization, that dynamically things get stuck. This is mathematically speaking not quite the same. In fact, one is in a way even stronger than the other, but there's this nice dichotomy of static localization, like eigenvectors have short-range correlations. Oh, hello. Haven't seen you in a while. And dynamical localization, that you have a particle, it will propagate a little bit, and it will get stuck along the way. So this is kind of this dichotomy of localization in the standard, in this well understood notion of Anderson localization. So does localization survive finite interactions? So on top of having this order, you put a bit of this interaction in. Does that survive localization? And to the puzzlement of some, or to the excitement of others, indeed this is the case. And this is what is called many-body localization, where you have not only disorder in the system, but you also add interactions, like in the fermionic model, would add interactions to this model. This is a type of setting that's intriguing, is extremely rich physically. It has created an enormous interest, mostly among theorists, also by due to work by Hughes and Paul, in fact, who kind of put this problem back on the agenda. That's an explosion of interest in the subject, but at the same time, it seems fair to say, or hope, that it is still far from understood of what the essence, what the basic founding ground of that phenomenology of many-body localization, after all, is when you look at it. So there's huge communities that are interested in that field, in that problem. However, depending on who you speak to, and there's kind of the 10 people in the room, 10 opinions on many-body localization, different people would put a different emphasis on the subject matter, and sometimes it always looks like as if they would be talking about different fields, so to say, because a different emphasis is put on the phenomenology of what is the defining feature of MBL after all. And this is kind of these different pictures of MBL that we will have a look at in this talk. So let's have a look at a number of pictures of that kind that people have been discussing in the context of many-body localization. And some of them we've already seen or touched upon in the nice talk of Romain earlier this week. So one statement is, that's kind of this Princeton school says, a system is many-body localized if it fails the eigenstate thermalization hypothesis. If it doesn't thermalize, so a system would be called MBL if the ATH breaks down. This is a very beautiful, very physicsy understanding of the phenomenon. You relate it to a problem in statistical mechanics. The system is MBL if it gets stuck and does not thermalize and does not form its own heat bath. So it's very operational, very physicsy, very intuitive, and very beautiful in many ways. At the same time, it's also a bit kind of intriguing in the way that the eigenstate thermalization hypothesis is a hypothesis after all. So it could be that it's not quite valid for all systems. So in this sense, any system would be MBL in a way that all systems do not fully satisfy the eigenstate thermalization hypothesis. So it could be a kind of a tautology that all systems happen to have that feature, and then it would not be a definition of MBL. I don't want to be critical. It's a beautiful picture. I'm just saying that it possibly does not grasp the full phenomenology of the phenomenon, which is, I hope, is a fair statement to say. A more physicsy picture coming along with that goes back to seminal work by Basco, Arena, and Altschuler, who looked at the non-interacting problem and introduced interactions as a kind of perturbation. They solved the single particle problem and built a Fock space of Slater determinants out of that, and considered what could be called like localization in Fock space on the graph that relates to the Fock state problem, arguing that in the presence of interactions, the localization effect would maintain, and there would be many-body localization from this perspective. It's a beautiful paper. it links like a deep physical intuition with a chainsaw massacre of combinatorics. It's a very hard read, but it's really a beautiful piece of work in physics, arguing that localization would be maintained even in the presence of interaction. Now, building upon that, there has been numerical work by Nariak and Bauer, who argued that if one looks at the many-body eigenstates of a many-body localized model, then one could relate these many-body eigenstates, and not only the ground state, but all the way up in the high energy levels, one could relate these eigenstates of the many-body Hamiltonian to a Slater determinant with a short-range quantum circuit. In other words, not only the ground state, but all the way up, the many-body eigenstates would have little entanglement that would be characterized by area law entanglement, as we also heard in Ludwig's talk this morning. Would be like short range, but not only the ground state, but all the way up you would have like an area law eigenstates, you would have matrix product states that capture the many-body eigenstates of the MBL Hamiltonian. They took it as a definition, the system is MBL if not only the ground state but all the way up, one would have like at least many of the eigenstates would be matrix product state eigenstates and would be characterized by area law, short range entanglement, and that's corroborated by beautiful numerical work by the Toulouse group, who indeed found that, say, up to mobility edge, you would have the situation that indeed there's a kind of an area law type entanglement in the many-body eigenstates, as opposed to a volume law that you would generically have if you go to a shop and buy like generic states in the bulk of the spectrum, you would get Haar random states. Not so in the MBL case, where you would have like area law states even high up in the spectrum. So this they took as a definition. A system is MBL if there's kind of matrix product states eigenstates in the many-body Hamiltonian that can be seen as a static definition of MBL, beautiful in its own right. So that's kind of the static reading of MBL, yeah.
I heard this thing times, but I never understood. Is it the area law of the single realization of disorder or after average?
No, the single realization. It's a statement with, okay, the paper as such, but again, I don't want to be critical. They're talking about most states without really fully clarifying what most means, but I mean, what it eventually is, you take a realization, a disorder realization, you look at it, and then you make an argument like with high probability over the disorder realization, you would have the feature that the eigenstates, many of the eigenstates, or most of the eigenstates, in a sense we may precise, would be area law. But it's not no disorder average, but it's a typicality statement. It's like with high probability over realizations, you would have the feature such that, right? It's not no average. Average would be weird. I mean, I don't even know what that would mean on the level of individual eigenstates, because it goes all crisscrossy. No, it's really, in short, every realization will have that. That's the very blunt answer. No disorder average. Does that, are you happy?
Yeah,
good, very good.
I believe it.
Good, very good. So these are kind of static definitions. I mean, besides, I have slides, but I don't have to come to the end. I just stop when it's 4, right? So don't worry.
Keep on going.
Yeah. Okay, so these are the static readings of MBL in the way of like properties of the eigenstates, quite reflecting what we heard of on the Anderson case of eigenstates being short range and so on. So it's kind of the many-body analog of having area law eigenstates, short range clustering. It's a kind of entanglement-based manifestation, but in spirit, this would be quite close to the static reading of localization in the way that we very beautifully understand in the Anderson localized case. So that's the static reading on the one hand. More dynamically speaking, people have looked at properties. Oh, this is some work that we did with these gentlemen here. Yeah, on total correlation, that's a kind of beautiful way of getting better the ergodic to localized phase transition. If interested, ask me about it. Yeah. So these are kind of static characterizations of that. More on the dynamical side, people have been looking at what happens, say, if you quench a many-body system out of equilibrium. Very much in the spirit of what we've heard many times this week. You quench and you see what happens and say, how does the entanglement over time behave? Now again, relating to the copyrighted beautiful picture of John, we would expect in an ergodic system that through this kind of light cone picture that we all know, even if we close the eyes, we would over the cut see that there's a linear growth in entanglement over time, just because of the quasi-ballistic, the quasi-particles ballistically coming in and the entanglement growing linear in time. So generically one would expect a linear growth entanglement, one that one easily sees in numerical approaches, which is precisely the reason why MPS simulations go down in time if one wants to push it in time in the way that Ignacio has beautifully explained earlier this week. Not so MBL systems. MBL systems will have a growth of entanglement in time, but this will be slow. It will be painfully slow. It will be a logarithmic growth in entanglement. If you quantum many-body system, that's a kind of a fast phase, and then will be very slow and will be logarithmically growing in time. And well, this is what it is. So this has been observed in time. And of course, this also means why one can go to larger times numerically, because there's kind of less entanglement in the system. So what would be a dynamical reading of localization anyway in this more general context? So the most stringent definition of dynamical localization I can think of would be just a Lieb-Robinson bound, but in this case a zero-velocity Lieb-Robinson bound. They come in different forms and flavors. So a most natural one would be where you look at the Heisenberg picture evolution of an observable and look what error you make if you evolve that under the full Hamiltonian and a truncated Hamiltonian as a buffer region around that Hamiltonian. And if this error is exponentially small in the size of the buffer region, you would say you have a zero velocity Lieb-Robinson bound. That means you hammer here, stuff can get a little bit across, but it will not get across the entire lattice. So this is the most stringent form of localization. In fact, the Anderson model has that feature with high probability. For a many-body localized model, this is presumably slightly too strong. But well, this is the most stringent form of dynamical localization. Then one can think of the absence of particle transport, allowing for like phase stuff to get across, but you would say particles, as fermionic particles say, would not walk too far up to an exponentially small tail, but that's uniform in time. There would be a way of capturing no particle transport, but possibly phase transport in the model. And finally, one can think of like having a mobility edge, and you say there's a certain energy level in the many-body system such that in the low energy sector you would have no propagation, but high up you can have that. This is something that's very reasonable for in the MBL setting, where you say in the low energy sector you would not have propagation, which you can also make operational, that if you are initially in that low energy sector and you make a local unitary, then stuff will not get across, but in the high energy sector this may well happen. This kind of dynamical localization with a mobility edge that is perfectly reasonable. So I'm 33 minutes into the talk, and shocking, and come to the kind of core question of the rest of the talk, which is, how are these pictures related? So let's, for a moment, not do new physics. We do this at the very end a little bit, but not to do the opposite in a way. Just look at all these pictures that are together, all this kind of this diagram of all these different pictures of logarithmic entanglement growth, suppression of transport, information propagation, area laws, Fock space localization, local constant motion, absence of thermalization, this beautiful plethora of phenomenology that kind of seems to be unrelated, and carefully have a look at that and play the cleanup man, the kind of the mathematically minded trash man, to kind of see how these pictures are related and not see that they come together, they're not in a coincidence, they don't kind of pop up in one way or the other, but in fact they're consequences of each other. So this is, even if I skip some of the mathematical details, I will, for reasons of time, if I may, I will not cut short the emphasis of this program, that we have this diagram of all this rich phenomenology of many-body localization, and would like to draw arrows into the diagram saying that some property is more fundamental, deeper than the other, because you want to relate these features as one being a consequence of the other in the sense of a mathematical theorem. To kind of clean up the richness, positively put, and the bit of the mess, negatively put, that comes along with this rich phenomenology of many-body localization. That's kind of the program that we have today. I mean, every talk has to have some sort of message, and this is kind of the message, that you can kind of clean up this diagram a little bit. So let's go through the diagram. I have like 4 examples. Yeah. Okay, let's see how it goes. So let's see, for example, how can the dynamical picture and the static picture be related? In Anderson localization, it's very much one-to-one. This is in a nice correspondence with each other. So how can you argue about the dynamical reading? You hammer here, things will get stuck. 2 eigenvector properties of the many-body Hamiltonian, like a static reading of many-body localization. How do these pictures come together? So there's these blobs to the left. You want to kind of draw a diagram here. So are the dynamic pictures and static be related? And the answer is yes. Oh, that looks horrible. But I have already made the answer. The answer is yes. Namely, rather look at me than at this slide. Right? The thing is, if you have dynamical localization in the sense that particles don't get across, like in the zero velocity sense, in the most stringent sense, then you find that not only the ground state, but in fact all eigenstates of the many-body Hamiltonian will have exponentially clustering correlations in the distance, again in the way that we saw at the beginning of the talk. So in this very strong sense, like in the Anderson insulator, you would get an exponential cluster of correlations, not for the ground state, but all the way up. If you have a Hamiltonian with a mobility edge, where you only in the low energy sector would have that feature, that would still be true that not only for the ground state, but the way up to the mobility edge, you would have, although in a slightly more complicated way, you would have again clustering of correlations in the distance. So this kappa is a parameter that can be tuned to make the bound optimal. So the thing is, the static and dynamical localization is not kind of coincidental, kind of not looking together, but if you have dynamical localization, say with the mobility edge, it means that you have short-range correlations in the many-body.
These does not imply area law.
I will come to that. Thank you for the question. So I have a bit of, yeah?
Just understand, how do you define this transport? I mean,
in the way I had on the previous slide. Like either zero velocity Brownian bound, that's the upper part, the A, in the B part, no information propagation on the low energy sector. That's precisely what I mean. And under these assumptions, this follows. And there's no extra assumption going in. This is just the only assumption that you have. Thanks for the question.
What is the AB there?
Oh, these are observables on A and on B. These are kind of correlations of observables in the lattice.
But what stays in the exponential is the distance of the support.
The distance is some graph, and then it's like the distance in the graph. Like in 1D would just be the number of sides you have to walk in the lattice. Just in exactly the way Benjamin had in his talk. I think even had the same symbol. It's just the standard clustering of correlations definition. Yeah. Okay, the proof I cut short the proof techniques are a bit similar to the ones that show the stability of topological order in the presence of local interactions. So there's these filter techniques that keep a compromise between locality in the lattice and in energy space. So this kind of these energy filter techniques in Lieb-Robinson bounds to, well, in a way to use a combination of high-pass and Gaussian filters to sneak in a commutator in the expression such that one can make use of the Lieb-Robinson bound or the weaker version in one way or the other later. So this is I will maybe cut short. But the point I will not cut short is you hammer here, you have a dynamical localization. That means that the system will have clustering of correlations not only for the ground state but all the way up. What is more, this short-range correlations one can, to come back to Pasquale's question, can relate to having actually an area law. This can be made more stringent, that not only do the states have clustering of correlation, but in fact they fulfill an area law for the entanglement entropy, as we beautifully heard in the first talk today. Again, not for the ground state, but all the way up. And in 1D, that even means that these states can be well approximated by so-called matrix product states, as Ignacio has explained in his talk, with a small bond dimension, which is this wiggly virtual parameter that he beautifully explained. So again, that comes to your question. Indeed, in 1D, you would have that not only the ground state, but all the way up, you would have matrix product eigenstates with a small bond dimension that capture the many-body Hamiltonian. So in this sense, this Nayak-Bauer picture that they argued on the basis of numerical considerations, that's in a way a provable consequence of having dynamical localization. It's not kind of coming together, but in fact it means that if you have this kind of dynamical non-spreading, you will have that many of the eigenstates are indeed matrix product states, giving further corroboration to the static reading, this Bauer-Nayak picture of MBL as having matrix product eigenstates all the way up. Does that answer your question?
It's not clear why, but okay.
No, it's not clear why. But yeah, I give you the details of the proof. Yeah, but I'd rather move on. But I mean, this is I can. It's a variant of an argument by partially by Verstraete and also.
The point is independent of the exponential decay of causation. That's what I was telling. Things are not related.
No, one is a consequence of the other under certain conditions. This is fine print. But in 1D, a certain type of exponential cluster correlations can be related to an area law. Because we make actually, Ignacio has explained that.
State is
Sorry?
A finite temperature state that has exponential decay.
Yeah, it's a pure state.
Volume law.
Pure states.
You can come from a pure state.
Yeah, okay. I mean,
by something.
Okay. It's a variant of an argument of doing sequential singular value decompositions and making sure that the error you do in each step doesn't accumulate too much. And then you kind of do it sequentially and you kind of break it down in a matrix product set. It's actually quite in the way that Ignacio has explained. So in a way I can make a reference to his sequential MPS. SVD, let's discuss that later. But I mean, this is a kind of a variant of a standard technique, yeah.
This dynamical localization is compatible with any sublinear growth of the entanglement?
Yes, indeed. And we come to that in a second.
You just know it's sublinear, it's not logarithmic, clearly.
Yeah, indeed, that's correct. Okay. This is correct, but that's actually the next question I wanted to ask. Okay, that's good. Yeah. So, okay, again, dynamical localization means that it's not a coincidence, not a kind of I mean, I made my point, right? It's really a consequence that if you have dynamical localization, it means that you have this many-body, this eigenstate static localization in the sense of matrix product eigenstates, further corroborating this Schetter-Nayak picture. So transport variation propagation can relate to area loss. Good. Yeah, okay. In another picture, yet another way that people say as a defining feature of MBL that relates to this integrability theme of our workshop is that they say a system is MBL if there's n constants of motion of the system which are not precisely local but approximately local, like up to exponentially small tails would be local, not quite in the same way as Benjamin has explained, because there would be translation variant, or like Tomasz keeps iterating, but they're really approximately local in the lattice and stick there. So people say a system is MBL if it has n linearly independent approximately local constants of motion. Can you derive something from that? Indeed, one can. Indeed, one can find MPS eigenstates, and something a bit stronger even. One finds that not only the eigenstates are matrix product states, but in fact all the full Hamiltonian is a one-size-fits-all tensor network state, a so-called spectral tensor network, where there's additional indices that specify what specific energy eigenstate you have, but there's one tensor network for the full Hamiltonian that you can write out as a one big, say, matrix product operator if you want. So this can be used to efficiently compute things of the many-body eigenstates, but you could even sample from Gibbs states efficiently in this way, and that very nicely compares and relates to Ignacio's talk where he did numerical computations there, because the basis of the functioning of that is that you have the spectral tensor network of the many-body Hamiltonian in the first place, and there are several variants by which you can make this a functional method, for example, by directly using this diagonalizing unitary, or you can directly look at the constants of motion as a matrix product operator representation. The thing is, if you have constants of motion, which are approximately local, it means that you have a matrix product representation or MPO type representation of your full many-body Hamiltonian. That's another error in our diagram. So local constant of motion, or approximately local constant of motion, again mean this kind of reduced description complexity, this area law type thing. Again, you have this reduced complexity. So we have already 2 diagrams, 2 arrows here. More arrows. It also means, to relate to your question, how about entanglement growth? One can show that if you have approximately local constants of motion, then at most the entanglement can grow using a result by Kim, Chandran, and Abanin in conjunction with a result by myself and Tobias Osborne, that the entanglement can grow, but at most logarithmically in time. It's another statement. So if you have approximately local constant of motion that people take as a definition, again, this log growth of entanglement, or at most log growth of entanglement, is again a proven consequence thereof, and it cannot grow more, although it could in principle grow less, as has been suspected already. And then, of course, you can relate to the absence of thermalization, but that's rather obvious.
Are there assumptions other than local constants of motion?
No. Approximately local constant of motion, that's enough. No, and linearly independent, and you have enough of them.
I think I could have an integral model that was translationally invariant, no MBL per se, and I could write the basis of the charges of integral motion.
Ah, but be careful, that was the comment I made earlier. This is often confusion. It's approximately local constant of motion in the sense they sit somewhere, and the truncation error, if you truncate, would be an operator norm exponentially suppressed with a distance. They're really on the side. That's sitting on side 17. It's not like of the type e to the power of phase and shifted terms. It's not of that type. That would not be MBL. Like a standard integrable model would not be of that type. It shares features of integrability in the way that Romain has nicely explained, but he's already gone. Yeah.
Usually the charges in an integral model aren't written in a local way, but one can write them in a local fashion.
Well, I mean, it is what it is. I'm saying if you have linearly independent constants of motion for which you have as many as you have degrees of freedom, and you have exponentially suppressed tails, then you find a spectral tensor network.
So do you think you need an exponential number of these charges?
No, linear number. Yeah. So this is what it is, and then we can together explore the diagrams, the consequences there. But this is a theorem, so we can talk about that. Yeah. Okay. So let me then. Otherwise, I'm running out of time. Yeah, I'm already running out of time. Let me have a final example. Oh, that's a shame. I had so much nice new material also related to experiments at the end. But anyway, I'd rather make this point. This is a bit of an interesting thing. So let's look at the converse direction of, we said dynamic localization means static. Short-range entanglement, short-range stuff, area law. Is the opposite also true? That seems totally plausible. Say if you have short-range entanglement or constant of motion, does that mean that you suppress information propagation? Things get stuck. You don't get across from constant of motion or from short-range entanglement. That seems totally plausible. So what about the converse error? Yeah? And so here's the thing. Let me define information propagation. That looks a little bit fanciful. Maybe I say that rather in words. It will convince you in words. Maybe if this looks a bit funny, whatever. I'm just saying I have an observable somewhere and let it evolve in the Heisenberg picture. If I can make an arbitrary large buffer around that and find a signal outside the buffer region that's arbitrarily large, I would say I have information propagation. Right? I mean, I have a site here. I put particles here, say. And then I make a huge buffer region around it that's kind of 10 kilometers large, and I can say, if I make a measurement outside that region, and if I can detect at later times whether I've put the particle there, then I have information propagation.
For any observable.
For a suitably picked observable. Yeah. But this is like what quantum information people would call a channel capacity. Is really a communication channel. I put the particle here, and I can do Morse code saying, I come home late for pizza. I can put this with the particle, and I would make the measurement, well, stupid jokes aside, I'm saying there's a communication capacity by making a local change in the lattice, and you would make a suitable measurement arbitrarily far away. And if this only decays Pauli in the distance, you would say you have information propagation in the system. I mean, this way put, I think it's perfectly plausible, and that's what this impression says. And this also implies a classic information capacity of the channel if you really want to make it quantitative in the sense of a channel capacity. So this is what I say a system has information propagation in the lattice.
I mean, then we have the equal time, so...
No, at later times.
Okay.
This can be later. You put it somewhere, it's in the Heisenberg picture, and then you wait for long times, presumably, and then you measure. Because initially, I know there's a result of 0. Exactly. You're absolutely right. Yeah. That means it's the Heisenberg picture evolution. So one would say, or would think, intuitively, that if you have like constants of motion, that would prohibit information propagation of that type. Yeah? So the following statement is true. It's again a theorem. Okay, you have a Hamiltonian that has a generic spectrum, which just means no funny degeneracies, nothing else. It's just about degeneracy of the spectrum. Okay? Then, if either of the following is true, say the Hamiltonian has product eigenstates. Wow, it's a very special Hamiltonian. Okay. Or it has an exactly local constant of motion, or maybe many, but at least one. Okay, or there at least exists at least one, but maybe linearly many, approximately local constant of motion. That's precisely what MBL is as a defining feature. So if you have like at least one approximately local constant of motion, you would think that this would pin down stuff, it narrows down stuff. If constant of motion, it suppresses things get not across. That's what I would intuitively think. So this is the assumption. One of them is true, for example, at least one approximately local constant of motion, but maybe many. Okay, if this is true, then you have information propagation. You must have it. This is kind of intriguing if you think about it. You have a system that has approximately local constants of motion in arbitrary model, any MBL model, whatever you have, it just has to have at least one approximately local constant of motion. That's your assumption. And then, if this is true, you can prove that if you make a suitable local excitation, this has to give rise to a signal arbitrarily far away that you can measure and has information content.
If you take an Anderson insulator,
I said, I was very honest about it. I said generic Hamiltonian, which just means no degeneracy in the spectrum. The Anderson localization will have, because the free model would have not in the spectrum, but in the degeneracies have funny degeneracies in the spectrum. That's it. That's why it's not an example, but otherwise an arbitrary generic Hamiltonian. That's the...
Why is the degeneracy? It's a random.
It's a free model. It's a
the energy are random.
Yeah, but think about it. The energy differences are not random. The gaps of the gaps are not random. It's a free model. You're absolutely right. The energies are random, but you get what's so-called non-degenerate energy gaps. You get degenerate energy gaps.
You have a decoupled site in a magnetic...
No, it will not be generic in the spectrum. You get degeneracies. Trust me. Totally. We thought the same. But think about it for a minute, and then you get a degeneracies. That's just it. Otherwise, if you uncouple spins, they get you in the gaps. You get degeneracies. That's the thing. The same thing as is this. This is the same argument. Go to free model decouple. It's the same argument. Yeah, we speak in a minute. Okay, but this is the only assumption. But this is kind of a curious. I mean, it's not so deep maybe, but it's a curious result that just from having local constant motion, you must have information propagation in a model, which is perfectly compatible with MBL because you have this log growth of entanglement. But it's not a coincidence, or it's not compatible with, but it's a consequence. You must have it. If you have a constant motion, you must have the possibility of getting stuff across, and you cannot keep it together. This is kind of...
Sorry, I kind of don't understand exactly what the theorem means.
Okay.
If you are in the MBL phase, you transport information. That's what
yeah, okay. A very physicsy way of putting it is, if I'm the MBL phase, there must be information propagation. Yes. Here, what's really literally stated is you have a Hamiltonian that has at least one, or maybe many, approximately local constants of motion, and then it means you have to have information propagation, which is not in contradiction with anything, because you have this slow growth of entanglement, which is compatible with constant motion becoming entangled over time, but it's not a coincidence. You have to have it. That's the
curious. You're saying that the MBL phase doesn't transport particles, all right?
Yeah, exactly. It doesn't, but information. Exactly. But this is a kind of a rigorous way of capturing that intuition that...
Does it mean that the MBL phase